Okay, let's make a start. Wow, I see we should maybe give you the real exam today. Only about 50% of the class will be taking it. Okay, so today I want to move into the middle third of the class. A couple of announcements. So the grading is ongoing for the exam and, of course, all of the assignments. Of course, you handed in a lot of work last week, so please give the GSIs and the readers a little bit of time to work their way through that. Also, so that you are aware, those of you who are in William's group, GSI group, William had an accident over the weekend. He was run over by a car. He's okay. But he was seriously hurt, and I think he's back home now. He was in the hospital for a couple of days. Anyway, so we obviously will figure out how to handle that, but I just want you to know that he's not obviously going to be available to you this week, so please don't start hounding him by email or otherwise. Obviously, he won't be having his office hours this week. We'll figure this out, and we'll let you know what we're going to do. But just so you know, so William obviously is not going to be around for this coming week. Okay? Any questions following the exam or anything else for that matter? Yeah. So the question is there any way we can post the answer key to the midterm? So no, we're not going to do that, I'm afraid. You're welcome to go and talk to your GSI, meet with your GSI, and he'll take you through the exam and you can look through the exam. But we're not going to just sort of post all of the answers. Any other questions? Okay, so let's get on. Sorry for being a few minutes late here. So let's jump in quickly to today's class. So we're now in the middle third of the class. And so the first third was really largely to motivate what we're doing here in terms of understanding earthquake processes. And then, of course, towards the very end of that first third, we started to talk about the science, if you like, the physical processes that are behind earthquakes. And we're now going to move into that wholeheartedly for this middle third of the class. So we're really going to be looking at the science of the earthquake process for the course of the next few weeks. And then, just so you know what's coming, then in the final third of the class is when we move on to talking about how we reduce the impacts of earthquakes. So once we've covered the science, we understand the process, we'll then talk about what remedies are available to us to reduce the impacts of these future earthquakes. So that's the overall scheme. So today I want to talk about the process of building up to an earthquake. You'll recognize the first few slides, but talk about how we make observations of the process of building up towards an earthquake. So you, of course, are all familiar with this. This is just to remind you, this is elastic rebound theory. This is all the earthquake cycle. People can call it various things. But this is the process whereby stress builds up on a tectonic plate boundary on the San Andreas fault, as in this example, because the Pacific plate is moving in this direction, the North American plate is moving in this direction, and so stress builds up between those two plates. It builds up, causing an S sort of shape to appear across the boundary. We're going to see more examples of this. And then once the fault can no longer withstand the stress, it pops, and that is what the earthquake is, and then this sort of S shape disappears, but it obviously doesn't offset those being created by it. Yeah. Okay. Outrageous question. The question was, for the next midterm, what's in the next midterm? Was the question, right? So the next midterm will cover all the material from 3 minutes ago until the next exam. Okay? All right. Okay, so this is the earthquake cycle. So the earthquake occurs, and of course the plates continue to move, and the stress builds up again, and then we have another earthquake, and on goes the cycle. You're all familiar with this. Okay, so how can we now actually make observations of this process? That elastic rebound theory was proposed in the 1906 earthquake report that was published, I think, in 1908, if I remember correctly. So that whole concept, this elastic rebound, was recognized and developed 100 years ago, more than 100 years ago. Okay? Before we had things like GPS and all of the modern-day techniques that we have to determine motions of the surface of the Earth, they managed to identify what was going on. So how did they do that? So the way that they did it was with geodetic surveying. Okay? And so there are 3 ways that you can kind of survey and understand the relative positions of points on the surface of the Earth. And then, of course, if you come back a year later and you remeasure those relative locations, you can get a sense of whether they are moving or not. Okay? So the first is what's called triangulation. And in a way, this is kind of the easiest thing to do, and it's certainly the most easiest way to see how you would be able to do that. Triangulation is simply measuring angles between things. That's what triangulation is. And in the case of mapping out the deformation of the surface of the Earth, what you can do is you can go up to high peaks where you can see other high peaks that are at some significant distance. Of course, the greater the distance that you're looking, the larger the deformation is going to be, right? So that's why you want to be able to see as far as possible. And so what triangulation means is that if you stand here at the top of Mount Tam and you look down to San Bruno Mountain and you look across to Mount Diablo, both of which you can see most days from the top of Mount Tam, you can then measure the angle between the line of sight to Mount Diablo and the line of sight to the San Bruno Mountain. Okay, so this is one of the first ways that people would start to map out deformation or map out positions, relative positions at the surface of the Earth. Okay, and so then you do that 1 year. You would then come back some number of years later, and of course you would expect it to be exactly the same because the surface of the Earth doesn't move, right? And of course what they found was that it had changed, and after some period of time they finally figured out that this wasn't measurement error or something else going on. This was real. The surface of the Earth actually was moving. So when you look at this, if you were to come back, whatever, 5 years later, 10 years later, would this angle that we're measuring here, would it have increased or decreased? So everybody look at it, and everybody think about it. Everybody think about how they think these points are going to move, and then decide whether you think it's going to increase or decrease. I'll give you a minute. And you're welcome to talk to the person next to you. I see many of you are not. I mean, many of you are. The rest of you are welcome to as well. Okay, so let's take a vote. Please be honest. So who thinks that this angle is going to increase? Who thinks that the angle is going to decrease? Okay, all right, that's right. The angle is going to decrease. So can somebody explain to us all why it will decrease? How about somebody from the back half? Nobody? Yes, go ahead. That's right, exactly. Okay, so of course these 2 points here are essentially on the same block. If you think of blocks of crust, right? This is one block of crust. There's the San Bruno fault. I'm sorry, the San Andreas fault, and then there's the Hayward fault and various other faults. But these are the various blocks. So these 2 are on the same block. So we do not expect these 2 points to move with respect to one another, right? So think of this as being fixed. Now if we go over to Mount Diablo, all of these faults are right lateral strike slip faults, and so that means that over here is moving down, while over here is moving up. Okay, so these 2 are fixed, but this point is moving down to the southeast. Then as this moves down to the southeast, this angle is going to get smaller. Okay? So one of the first ways that they recognized that there was motion going on across these plate boundaries, and it's not necessarily, of course, when an earthquake occurs, you would see motion, but you will see this motion even without earthquakes because of that deformation, that S shape that I keep emphasizing. So this angle is going to decrease. Okay, so the second approach is trilateration, which is about measuring distances between peaks. Okay, so now you measure how far Mount Tam is from Mount Diablo and how far that is from San Bruno. Okay, so now that you all understand how it's going to move, these points are going to move relative to one another, let's start with this line, Mount Tam to Mount Diablo. Is this distance going to increase or decrease? Increase, right? If this is moving down like this, then this line is obviously going to increase. Is this line going to increase or decrease? It's going to stay the same. And is this line going to increase or decrease? I think I heard both answers. Okay, who thinks it's going to increase? Who thinks it's going to decrease? Who's not sure? Okay, most of you didn't put your hands up, so I will put you in the not sure category. So this is a little tricky, right? Because this line, the reason this is tricky, it's not clear in the same way it's clear for here, it's not clear for this line, and the reason is that this line is sort of perpendicular to the orientation of the faults and the orientation of the motion, right? So it is actually going to increase. Okay, and the reason it's going to increase is that these 2 points, the line between these 2 points is essentially perpendicular to the fault, which is parallel to the motion. And so any movement of this is going to increase the length of this line, but only very slightly. Obviously, as this point goes further and further south, and this line here rotates around to be like this, and then like this, then the increase is going to get greater. So the point is that if you're measuring the distance between 2 points that are perpendicular to the fault, they're not going to change very much. Whereas if you measure the distance between 2 points that are oblique, or even more oblique, if it was from Mount Tam down to here, then it would change a lot. Right? So the amount that it changes is dependent on the angles. This is obviously a trigonometry problem. Okay, so that's trilateration. And then the third one, of course, is the other dimension, the vertical distance, and that's just called leveling, where you understand how much higher one point on the surface is relative to another point on the surface, whether they're at the same elevation or different elevations. Okay, so here's some actual data that comes from the oh no, it can't come from the report. So this comes from 1959 to 1970. But again, this is being done before we had all the sophisticated technologies that we have today, and it sort of illustrates what we've just been talking about. This is trilateration data, and so they have a whole series of points, the circles on this map. So here we are, just orange you. This is San Francisco, Berkeley's here. This is the Bay. Okay, so Hayward Fault right here. And then all of these circles are points where they have measurements, and then these lines are all of the measurement lines that they have. Okay, and so these plots over here are the 17, 19, 20, 21, and 23. It's these lines that are in bold over here. Okay, so let's start with line 20. This is line 20 right here. And so this 20 over here, this is measuring the change in length in centimeters as a function of time, and the years are marked up here. So from 1959 to 1970. So at line 20, the change in length starts at 0, and the change in length, or the length has increased with time. Okay, so how much has the length increased by? I assume you can all read the graph. How much? I heard somebody say 18. Okay, this should not be difficult. You're just reading off the graph. Why is there a hesitation? Somebody? How far? 16. Somebody said 16. So where are you getting 16 from? So here's 16, right? So this is 0, so it starts at 0. When we get up to the end of this period, what's this? 20. Okay, it wasn't that difficult, was it? Okay, so this has moved 20 centimeters conveniently, a nice round number. I mean, I know why you're having difficulty. I mean, who draws lines every 4 units? That's obviously insane, but there we go. So this is 20 centimeters, and it's gone 20 centimeters over how many years? 11 years. Let's make it easy. Let's say it's 10 years. So how far per year? I think most of you said 2 centimeters, right? 20 centimeters over 10 years is 2 centimeters per year, okay? So line 20 here has gone 2 centimeters per year. So now let's look at line 23, okay? So this is line 23 here. So this is line 23. How far has line 23 moved over this time period? Okay, so this has gone 0, 8. This is 8. Okay, so maybe it's up to 12. It's not as clear, this data. That's why we're doing this second. It's also been over a shorter period of time. So 1, 2, 3, 4, 5, 6, 7, 8 years, let's say. So let's say it's gone 10 centimeters, 12 centimeters over 8 years. How many centimeters per year is it? 1.5? Okay, so if this has gone 1.5 centimeters per year, and this is going at 2 centimeters per year, why is there a difference? It's not measurement error. Why is there a difference? What's the difference between line 20 and line 23? That's right. Line 20 goes across both. This is the San Andreas fault, and this is the Calaveras fault. Okay, so line 20 covers both both the fault systems, whereas line 23 is only covering the Calaveras fault system. So we're seeing less deformation. So the point is that line 23 is not seeing the deformation building up across the San Andreas fault. So that's why it's a smaller number. Okay. All right. So enough of that. That's how people used to do it. But I mean, it's informative to understand, sort of in a spatial sense, how the surface of the Earth is deforming. But let's move on to how we now do it today. Of course, the way that we do it today is GPS. You're all familiar with GPS. It's in every single phone, in every single pocket right now. And so GPS uses a constellation of satellites. In case you did not know this, GPS uses a constellation of satellites, 24 satellites that are orbiting in a relatively low orbit. And the way that your phone determines your position is using trilateration. It's actually measuring the distance from your pocket up to each of these satellites. And then by using the trilateration, it determines where you are on the surface of the Earth. When the phone is able to see the signal from 3 satellites, then it can give you the latitude and longitude location. When you have a 4th satellite, it can also give you an estimate of the elevation. Okay? The elevation accuracy is always poorer than the latitude and longitude, the XY location. And the reason for that is simply that the satellites are always, there's no satellite directly above you. The satellites are always at some distance, sort of low on the horizon in a statistical sense. And so it's much easier to get accurate locations sort of in the horizontal direction than it is in the vertical direction. To do a good job in the vertical direction, you would want a satellite directly overhead. And that's basically never the case. So that's why horizontal positions are always better than vertical positions. Of course, it's in everybody's phone right now. The accuracy on your phone is several meters. Okay? I mean, you can tell, if those of you who use your phone to guide you when you're driving, it's almost at the point where it knows which lane you are in when you're driving. Not quite, but almost, right? And so the width of a lane is what, 5 meters? And so it has an accuracy of several meters. Okay? Now, that's not much use for us because we're trying to measure deformation rates of a few centimeters per year. So we have to use differential GPS. You've already seen how we use differential GPS in the case of the Hayward fault. But with differential GPS, much higher quality receivers, stationary monuments that we then measure over long periods of time, days, weeks, we can get an accuracy of a few millimeters. Okay, so that's what GPS is for. You've seen what we can do with GPS when we look at the Hayward Fault, and you've seen this figure. This is looking at the stadium and actually seeing the deformation on one side of the stadium with respect to the other side. So these arrows indicate how quickly the eastern side of the stadium is moving with respect to the western side of the stadium. Okay, and so this is the creep rate, of course. So this is the ongoing creep. This is not the S-shaped deformation, and you'll remember that that's at 4 millimeters per year in the case of the Hayward Fault. So these GPS observations and this trilateration are how we measure all of these arrows on this map that shows the deformation across the entire Bay Area. You've also seen this map as well. And just to remind you that when we look at this section north of the bay, this is a locked section of the plate boundary, and you can tell it's locked because it has this S shape where we have these big deformation arrows at one end, and then big deformation arrows at the other end, and there's this S shape to it. I hope everybody can see that. That's kind of a key observation, this S shape that we're seeing here. And when you look at the creeping section, such as across the Hayward Fault, you essentially go, it's difficult to see, but these points here are showing no deformation with respect to Lutz. So these are stationary, and then you just step over the fault and you have relatively large deformations. This is the creeping section of the fault, which of course includes the stadium. Hang on, right, which the stadium. This is the stadium right here. Okay. All right. So let's look on a slightly larger scale. So this is now looking at the total deformation across the entire plate boundary, the boundary between Pacific and North America. And these are all of the observations points where people go and make regular GPS observations in order to track how the plates are moving on a continuous basis. More and more today, we use continuous real-time GPS stations. So Berkeley Seismo Lab runs a network of 20 GPS monuments that are permanently positioned, permanently streaming their data in real time, and we actually use it to detect the total amount of deformation that occurs during earthquakes. But there are many more points that people go back and they measure their position every year, let's say. And by measuring it every year, you can see the long-term plate tectonic motions. Okay? And so these are all the points where we do that. And then this is just a line of these points going from sort of the point that's furthest east and to the point furthest west, which is on the Farallon Islands, which are just offshore. You can see them if you look from the Berkeley campus through the Golden Gate Bridge. You can see the Farallon Islands out there. And so again, this is motion with respect to the center of North America. So as you get further and further away from the center of North America, these arrows get longer. And as you get all the way out, you see the entire relative motion of the Pacific plate over here with respect to the North American plate over here. Okay, so we actually see this motion going on. And the total motion across the plate boundary in the Bay Area is about 5 centimeters per year. You've seen that number before. Okay, but this is the data that tells us it's 5 centimeters per year. And so this is where I made this joke about what's going to happen to LA over the course of the coming million years. This is where that number actually comes from. So Los Angeles, of course, is on the Pacific plate. Okay? So it's on the western side of the plate boundary. San Francisco, right here, it's for the most part, it's on the eastern part of the plate boundary. There's still some deformation over here, so it's kind of in the middle. But for the purposes of this, let's just assume it's on the North American plate. Okay? So the distance between Los Angeles and San Francisco, which is essentially along the plate boundary, is 500 kilometers. The rate of plate motion is 5 centimeters per year. So you take 500 kilometers and you divide by 5 centimeters per year, you get 10 million years. So it's going to take 10 million years for LA to get up to the latitude of San Francisco. So that's where that number comes from. Yeah? Does the total motion change? What do you mean? Oh, this number. Oh, that's an interesting question. The question is, does this number ever change? Does it ever become 6? Okay? And the answer is that yes, it does. So but not on an annual basis. It doesn't change from year to year. Okay? So next year it will still be 5 centimeters per year. And for that matter, probably a million years from now, it'll still be 5 centimeters per year. But 10 million years from now, it might have changed. So anybody like to guess what has to happen on a global basis for these numbers to change? So we're now talking about plate tectonic motions, right? We're talking about how the plates are moving over the surface of the Earth. So what has to happen in a plate tectonic sense for the plates to start moving at different rates or in different directions? Any guesses? None? Oh, yeah. Right. Oh, sorry, say the last bit? Okay, exactly. So what would have to happen is that there would have to be some kind of collision between the plates that causes a reorganization of plate motions, whether it be a plate slowing down or perhaps a plate moving in another direction. And what is it that has to happen? What is a big enough collision? Well, it's when a continent hits another continent. The only way you can stop plates moving is when one continent hits another continent, and it still takes a long time, right? There's no ocean between India and Eurasia anymore. That ocean, it's called the Tethys Ocean, has completely disappeared. But still, India is moving north at 9 centimeters per year relative to Eurasia. But the point is, it's going to slow down and it's going to stop. So the ocean that was between those two plates, the Tethys Ocean, maybe like the Pacific Ocean, was moving at some rate, and now it's going to stop over the course of the next 10 million years. So it requires something on that scale to change this 5 centimeters per year, and it doesn't happen overnight. Okay, great question. Any other questions? Yeah. Good question. So the question, okay, so the question was, do all of the faults in California have to equal 5 centimeters per year? So the 5 centimeters per year number is the total deformation, the total motion rate and velocity between the North American plate and the Pacific plate. It's pretty constant as you go down the San Andreas Fault. The San Andreas Fault is really a pretty small fault boundary. I mean, it's not that long. Okay? And so basically it's the exact same number all along California. That means that when you then take a cross-section perpendicular to the plate motion, so this is one cross-section through the Bay Area, you can do another cross-section down here to the south or another one up here to the north, going across the San Andreas Fault system, it will always add up to 5 centimeters. Now the number of faults varies, right? So there's a lot of faults in the Bay Area. You get a little bit further south of San Luis Obispo, there is just one San Andreas Fault. And in that case, the entire 5 centimeters per year has to be accommodated by the San Andreas Fault. While up here, the 5 centimeters per year is accommodated by the San Andreas Fault, the Hayward Fault, the Calaveras Fault, etc., etc. All right, any other questions? Great questions. All right, let's keep going. All right, so that was GPS. The other technique that we use to map out the motions at the surface of the Earth is SAR and INSAR. So SAR, first of all, is just synthetic aperture radar. And all this means is that you have some platform